and thank you very much for coming all to the Waterloo Data Science and Data Engineering Meetup for our meetup of December. I first would like to thank our host of this evening, Shiny Ducks, for providing us with the space. So we have some volunteers of Shiny Ducks. We have Johanna, we have Tracy, and we have Khalid. Thank you very much. And then we also want to thank Microsoft for the sponsoring, for providing us with all the great pizza. And as always, we will have 2 items today. So we will start off with a talk about AutoML, and after the break, we will have a panel discussion about how to grow your career in data science. And before we will introduce Zia, Johanna also first still has some housekeeping items.
So I will not be carrying a mic, but I'm hoping you can actually hear me. There's enough sound being captured, so it is being propagated through the room. But hi, my name is Zia Babar. I'm a PhD candidate at the University of Toronto. I'm also looking after the engineering operations at a company based out of Toronto. We at the Waterloo Data Science and Data Engineering meeting try to bring topics which are topical, which are current, and which we feel that the industry, folks in the industry would actually benefit, acquiring new skills, learning. So there's a lot of studying that we do, and we make sure that there are things which are important. I should have?
Yeah.
Okay. One of these topics that is very topical is AutoML. The idea behind AutoML is we use machine learning for machine learning, as interesting as it sounds, but that is a very valid application of machine learning. So machine learning has been used to solve business problems, and this is one of the additional problems that machine learning can be used to solve. We have some resources, so if you go to this QR code, I'll have this QR code at the end as well, at the last slide, but this would actually take you to some AutoML resources. As Mary said, this meetup has been sponsored by Microsoft, so we'll be demonstrating some of the capabilities that Microsoft provides from an AutoML perspective. Yes, about myself. I have over 20 years of industry experience. I primarily deal with the development of distributed systems, data engineering platforms, applied AI. I am finishing up my PhD at the University of Toronto, and I work with different companies on research engagements. So there's a very famous saying, this was by Mark Anderson, software, So software is eating the world. This was said, I think about 20 years back or 15 years back. So sometime, around the dot-com boom or after that, where software was disrupting every industry. So software was actually transforming entire industry spaces, and that's where this phrase came about. Software is eating the world. Well, you know what? The NVIDIA CEO said a couple of years ago, yes, software is eating the world. It's accepted now after more than a decade of evidence. But you know what? AI is going to eat software. The idea behind this is that as AI becomes more intelligent, as it becomes more and more applied, so fields which were dominated by software engineers, well, AI is going to slowly substitute the need for software engineers to develop all of these software applications. Why do I say that? Well, AI is actually a difficult space to be in. As we all know, it requires a lot of study, a lot of investigation, a lot of experience or experimentation to get to a certain proficiency level. And I just put some, this is not based on any scientific survey, this is my opinion, but this is how it is, that you need to have a background in theoretical mathematics and algorithms, you need to know probability statistics, you need to know programming languages, you need to have a little bit of knowledge of distributed computing, because when you're trying to scale a model, a machine learning model, you need to just have distributed computing. So that's where distributed platforms actually come in, and then you need to have somewhat of knowledge of scripting, of Unix, because primarily we use Linux to actually write scripts. You can also do the PowerShell as well, Microsoft PowerShell. So these are areas that we require different levels of competency. None of it is actually easy to come by. Now this is from a researcher's perspective. As a practitioner's perspective, the degree of some of these circles, or the width of some of these circles has changed. You still need knowledge of applied mathematics and algorithms, probability and statistics, a little bit less because you're using these pre-built frameworks, these pre-built algorithms, and you're applying them. But your programming knowledge needs to be a lot higher. You need to learn lots of different languages. You need to know more about distributed computing because now you're trying to deploy it at scale. And of course, the other side of programming languages is you need to have scripting knowledge so that you can actually deploy things and make them run. So again, none of these skills are easy to acquire. It takes years and years of experience, of trial and error to actually come to a level of proficiency. This causes lots of challenges. So companies need a lot of AI talent. They are willing to hire a lot of people, but they can't find individuals. So they are trying to get individuals with some basic fundamental knowledge, who've gone through some online courses, who've gone and built certain models, who have a basic understanding, and then hopefully on the job they will get more and more proficient. So it's difficult for companies to hire AI talent. It's time consuming to acquire that knowledge. There are lots of competitive pressure. So someone who actually becomes good at this space, that person becomes exceedingly sought after in the industry. There's a lot of predatory tactics which are going on, where once you have established yourself, then you'll find different companies trying to pull you and trying to give you, pretty good salaries. Talent is rare, like I said, and finally it's expensive, both from a time perspective and for learning monetary perspective. It is exceedingly expensive. If you go for an advanced degree like a master's or a PhD, that's many years, tens of thousands of dollars. If you go for short-term courses, that's still tens of thousands of dollars. So it is very difficult and expensive to get this talent. One phrase that has been going on quite a bit is democratizing AI. What that means is you want to bring AI to the masses. You don't want this to be this exclusive club that people only with very advanced degrees or people who have a lot of time or money can only acquire. You want to bring this down to the enthusiast level. So someone who can spend a few weeks or a few months of effort can actually become an AI developer. That's the ambition, that's the hope. You want to make things easier for people to get into this. And the idea is that as more and more people get into this space, you'll have far more innovative products coming out. You'll have typical products which can be infused with some AI capabilities, some cognitive capabilities, and now someone has come up with a solution that is far better than what would have been there before. The number of people which exist in the world right now in Canada, there are not that many that you can actually go and disrupt each and every single space. So by democratizing AI, hopefully you can bring about that revolution. If you want to build Canada as an AI center of the world, this is something that we have to consciously do. We want to make sure there's a large talent of AI in this country. And finally, organizations want to bring AI. So organizations traditionally who are afraid to engage consultancy companies to make themselves more AI capable or aware, well, now if you reduce the cost of bringing AI into their products, they can ask their employees, software engineers, people with some kind of interest or background, to work on these products and make them more AI capable. So how do we actually democratize AI? How do we actually bring AI to the masses? There are two ways primarily. One is to have pre-built models, pre-built frameworks, which are there, which are available, whether paid or free doesn't really matter, but someone has done the work. Someone has taken this exceedingly complicated AI algorithm, machine learning algorithm, coded it, implemented it, and provided it as a framework that you can use. So in your program, you just write a few more lines of code, you call this framework, you pass it certain functions, and voila, you actually have the ability to do regression analysis. I remember the first time I wrote I wrote a multivariate regression algorithm. This is probably 12, 13 years back in C++. It took me about 2 months of coding to implement, and then it took about another month of testing. So about 3 to 4 months of actual effort of engineers to actually come up with a single regression implementation of a regression algorithm. And we did that because the company I was a what would we call a BI company, business intelligence company, a Teradata. So we wanted to enhance our data warehouses, our products, with these machine learning algorithms, and we wanted to use them as part of our application. So it wasn't going to be for public, it was for internal consumption. So we had to spend like 3 or 4 months of intense effort to get a single algorithm implemented that we could then use within the company. And now someone can actually write a program that uses regression analysis in half an hour because it's part of TensorFlow. It's part of many frameworks which are available already. So now the ability for people to do advanced statistical analysis on data is much easier. So that's the whole point behind democratizing AI. So that's this approach over here, leveraging pre-built capabilities. If you look at any cloud vendor, and I'll talk about Microsoft over here because that's the sponsor of the day. So Microsoft has this pre-built cognitive library. It's called Azure Cognitive Services, where you can do text analysis, you can do voice-to-speech conversion, sorry, text-to-speech and vice versa conversion, you could do image recognition, you could do video analysis, you could do all kinds of sophisticated analysis using just a few hundred lines of code. So it's exceedingly simple. Microsoft has done that for us. So now we can all become AI developers with a few weeks of learning and programming. Another way is automating the ML pipeline, automating the machine learning pipeline. By pipeline, I mean the sequence of steps that you need to do in order to develop a machine learning model. So there are several steps which actually you need to go, and I'll show that in a few slides over here. So that's how you go through to develop a machine learning pipeline. By being able to automate certain key activities, certain key steps, I can now make this much more simpler. And I'll show examples of that in a little while. But these are the two ways to actually, again, democratizing AI. So the topic of today is actually this: automating the machine learning pipeline, or AutoML. So what is AutoML? AutoML is an approach that simplifies the machine learning, the process of developing machine learning models. We can do so, we can automate key steps in this pipeline by applying machine learning techniques. What are those techniques? Well, let me show you. Okay, before I get to that, so I mentioned we try to bring topical discussion points in this in Waterloo Data Science Data Engineering. So this is an evidence of that. You can see how significantly it's difficult to read the dates, but this is October 2018. So you can see in 2018 onwards, there's been a certain upward curve or a spike in AutoML, and this is a Google trend graph. So this is exceedingly getting popular, how to actually leverage AutoML. There's a website, automl.org. This has a lot of approaches and papers on AutoML. You can actually go there and check it, and you can again see in the past 2-3 years, there's been this sudden surge of papers being produced on AutoML. It wasn't there before. So this has become very popular, and as aspiring data scientists, I would really encourage you to learn about it a little bit more. So I talked about automating the machine learning pipeline. So what does that mean? So this is a typical pipeline that I've depicted over here. So we have raw data that comes in from some data source. It's not relevant right now where it comes from, but it comes from a data source. We clean that, we transform that, we manipulate that in some way. And then once we have data in a manner that is prepared to our liking, for our need, we actually then do something called feature engineering, where we decide which features of this data are important. We do some kind of processing on that feature, and then we come up with those. If there's some construction of features that is to be done, if we want to, for example, if you have first name separate and last name separate and want to combine it together, then we can combine it and construct new features. So we can do aggregation and other kinds of manipulation on that. But this entire green area is where you do feature engineering. Now this is a fairly intensive activity. It requires a lot of individuals to spend a lot of hours and time to actually bring your data to a state where you can then apply machine learning techniques on that. Once you're done, then you actually select the kind of algorithm that you need. So you have these different categories of algorithms, and you decide, okay, I want to do this kind of analysis, so I should go with this category of algorithm. Now, within that, you can have hundreds of algorithms. There are a few popular ones that we all use, but literally scientists are coming up with new algorithms all the time, or they're tuning existing algorithms and having variants of that that serve different needs or different situations. So you can have literally hundreds of algorithms. Remembering where to use when and why is difficult. And then once you've selected the right one, then there are many parameters that the algorithm actually takes. So now you have to fiddle around with all of these parameters, and you have to run it and then see, okay, this is what my, based on whatever the metrics you're gauging the success of this algorithm, you say, okay, this is what I'm getting, and then you fiddle around with some other parameters, and then you run it again, and then, in half an hour later, you get the results from that new model, and then you'll see either the results are better or worse. And then say, okay, now if they are worse, then I need to do something else. If they are better, you say, okay, I'm going to continue doing this. And you keep going through that, through rounds and rounds and rounds of iteration until you finally get to a stage where you say, aha, this is working fine. This is acceptable to me. Now I'm going to productize this. I'm going to now take it into production. So this is how the machine learning pipeline works today. Well, let's take each step. Each step can actually be optimized. And how can we optimize it? By applying machine learning to the machine learning pipeline. So let's say we'll take a look at optimizing parameters. Now, as I was describing it, it probably came to your mind, hey, this seems a bit unreasonable where you're fiddling around with different values and seeing what the outcome is. Is it better or is it worse? Can't we apply machine learning over here? So if we go through these, if we automate this cycle, and because we know what our aspiring, what our output metrics are, and we know what can be qualified as a good model, so maybe we actually automate the step of fiddling around with different tuning parameters for this algorithm and seeing if it comes up with a result that is better or worse. So we've automated this step.
Excuse me.
Yeah.
Doesn't that already exist? I mean, with gradient descent.
Yeah, it
That's
does.
how you tune parameters.
Yeah.
So, I mean, that step exists in
It
AI.
is. So there are individual ways of doing so, but yes, you're right. Gradient descent actually does do that for you. Yeah, because you're trying to get to the lowest point. Yeah. So this step is known hyperparameter optimization. And then the selection of algorithm, again, that can be done. So if you have hundreds of algorithms, you can again automate that. You can cycle through one by one and come up with something better as well. And finally, the process of feature engineering, determining which features are right. So not just which features are applicable, but what should be the format of the data. Should it be a string? Should it be processed as an integer? Should it be, what would be the ideal data format that would result in the fastest model training? So there are lots of different things that can actually be done around feature engineering as well to make it faster. I just want to make sure that I'm on time. Okay. So yeah, so this entire optimization generally comes under AutoML. It's a phrase that we're using, how to automate it.
Well, question.
Yeah.
So, regarding cleaning the data, doesn't depend on the model you are using.
It does.
So that needs to
So
automate
because
too.
cleaning the data, you want to make sure the data, you prepare data in a manner which is conducive to the model that you're going to be using. That is correct.
So that is not subject to automation too. If you don't know the model, you want to figure out which one it is.
You need to prepare the data in a manner that is conducive to the model. So initially, let me show you how Microsoft have done that. The examples that I have selected, feature engineering was kept outside of it. So there was feature engineering done, but that was done manually. I'm not sure if it actually is linked to the model selection and then the tuning of the model, as far as Microsoft solution is concerned. And I've not used others for now. But so this is the one that Microsoft does. So they do a data set selection, they do an optimization of metrics, they consider the constraints which are placed on the AutoML, because you don't want this running for days and days and consuming cloud credits. So once you decide all of that, you throw all of this in automated machine learning, and then that spits out a final model or a recommended model. So this is how it is. So I would assume, based on this diagram and what I have seen, that they keep the data set selection and the cleaning separate from the actual automated machine learning. Which is not to say that other vendors like Google Cloud, which also has an AutoML solution, would do things differently. I once fiddled around with there for not something like this, but for an image recognition analysis. At that time, because the data set was different, it was just images. I just uploaded images to Google's AutoML, and it went through the entire process without having me doing any feature engineering. So there may be something that was inbuilt, where it decided what data was actually suitable for. But these are, again, very toy examples. They're very simple examples. There's nothing complicated about them. So yeah, I can't give a very conclusive answer. Whether an AutoML pipeline would pre-prepare data with the knowledge that downstream it's going to use this model to make sure it's that, and then when it's moving to a different category of models or a different type of model, then it would go back and re-prepare the data for that model. Yeah, I'm not sure right now. I doubt it.
And just one more question. Yeah. We can also create an ensemble of multiple models,
Yes.
like, because feature engineering and model building go hand in hand, right?
Yeah.
So we can do that.
Yeah, probably you can do that. In fact, I did see in one of the examples that they did create ensembles. So I don't think so they would experiment, at least the pipelines that I've seen, the solutions that I've seen, experiment on the fly and say, hey, what if I combine this with this and then see if this becomes better.
Yeah.
I believe they already have these pre-built ensembles that they apply to the data and see if that produces a better result.
Okay, pre-built
Yeah. Yeah. So that's a little bit about the background. So I'm going to spend a few minutes. So Microsoft has this solution called Azure Machine Learning. The URL is ml.azure.com. It's also on that QR code, so when you actually use that, scan that QR code on your phone, it'll take you to these resources. So, but if you go to ml.azure.com, you need to have an Azure subscription. The good thing is that this is in preview mode right now, so I believe it's free to use. So you can connect. They comes in two versions, basic and enterprise. I believe both of them are free until you are in preview mode for the basic and enterprise. The enterprise version is the one that lets you do AutoML. The basic version lets you do machine learning, but it does not have AutoML. I've been using this for the past 2 days. I've been running this for the past 2 days. My credits, monthly credits have not gone down. So I think we are okay. If you want to experiment with this, sure, it should be fine. So when you go there, this is the kind of layout that you'll actually see. As soon as you log in, you'll see, welcome to the studio, there are different things that you can do. I'll spend a few minutes navigating here. So home screen, notebooks is when you actually create these Python notebooks, or Jupyter notebooks. You can actually create them over here. And they have lots of tutorials here as well. So for example, if I go here, so you'll have some pre-built samples that introduce Azure Machine Learning. And if you prefer Python, you have them in Python. If you prefer R, you can see them in R. This is the version of the ML library. So this has nothing to do with Python. It's just a version of the ML library that we're using. And you can see some of these tutorials over here. So the tutorial I'm going to show you today was actually selected from here. I think it's one of the regression automated ML ones. This one, I just picked this. But there are many others as well, covering a range of topics. This tab is where you can actually create an AutoML experiment. And I'll go through this in a little while. If you want to design your own pipeline, you can actually do that using a visual designer over here. So you can drag and drop, you can create pipelines to actually produce some results over here. So that can be done using the designer. Assets, then we have a different category of options over here. Data sets is data that you've brought into Azure Machine Learning. So for example, I uploaded this data set which is used in one of my experiments, bank marketing training data set over here. Experiments are experiments that you actually create. So I have an AutoML experiment, it's shown over here. I have 2 of them actually, or 3 of them. That I'll go through in a little while. Pipelines is an unrelated to this AutoML, but essentially a pipeline is a machine learning pipeline. So you have different stages and you can actually create them. And I can create a new pipeline over here. So I can ingest data, I could transform the data. All of these steps are shown to me over here. I could run different statistical functions. And then finally I could output a model that I could run Python code. So this is a pipeline that you can actually create. Models are where your models are going to be, and then endpoints are how you actually connect to the model. So once you deploy a model, once you train a model and you're okay with it and you deploy it into production, you want to be able to connect to it. So these endpoints are how you actually connect to those models. So this is a very brief 3-minute introduction to Azure machine learning, and it's a fabulous tool, I would say. I mean, I've been looking at this for the past at least 5 years, and it's gone through many different stages of evolution. And this is the most refined that I've seen it ever to be. I really like it. So let's go to AutoML. There are 3 ways. Today I'll try to show 3 ways of actually creating an AutoML experiment. The first one is using the UI over here. So it's very simple, very straightforward. I say I want to create a new AutoML run. I select the data set. I've already uploaded the data set. It's already present over here. I give the experiment name. I say in my data set, what is it that I'm trying to predict? So this is a classification example, right? So I'm trying to predict the output value of I say the column in this data set, this is called Y. And then I say, where should this experiment will be run? So I've already created compute. Compute is where the code is going to run, the training model is going to run, the model training is going to run. So I provide that over here, and I've already, as you see, created one. If I didn't have this created, then I could create this very quickly over here in this option. But this is something that I created a couple of days ago. This is the classification analysis, so it's already saying, it's saying, do you want to enable deep learning, which means that do you want to apply deep learning classification techniques to this data set or not? You can, if you want to. I did not select it. If you want to do regression analysis on this data set, you can actually select it over here. If you want to do time series forecasting, you can do it over here. So I have classification, because this is a classification problem. I have a regression one in another data set, which I'll show how it's done differently. And then finish, that's it. So I created a machine learning training model over here. It is now going through the cycles, the iterations of training. Oh, by the way, I forgot, I made a mistake, but not a mistake, but there are advanced parameters as well. What that they let you do is define certain constraints or thresholds around what you want to do. Like, I don't want this running for 5 days. I want it to terminate after 2 hours. So if you converge to a solution within 2 hours, that's great. If you don't, then maybe you've just gone through 50 runs, and that's fine. Just show me the results of 50 runs. Just don't keep running forever and ever against thousands of algorithms that you have. So there are different kind of constraints that you can place, or parameters that you can define that would tell you when to stop this training, or what the convergence points should be. So that's another thing that can be defined. When would this be converged? When would it be good enough? So yeah, this is running. If you can see that the status is it's preparing right now. In a little while, once it's prepared, it will start running. When it's running, it will actually show you over here. When you click on models, you can actually see models come up in real time. So as it's applying each algorithm, it will tell you what the measure is going to be. You can also define what your criteria for qualifying these models are. So for example, over here it's accuracy, but I could use something like AUC and say that, okay, show me the one which has the best AUC, A-rank curve. So things like that can actually be defined. Duration and stuff. Let me show you one that has already run that I did previously, so you can see what I'm talking about. So this is something that I ran a couple of nights ago. So if I look at the run, so it finished. So this is the summary, or this is the output. It told me the best or the recommended model was voting ensemble. So this is the ensemble method that it actually detected. I don't know what it does. It's there. It found this out. My evaluation, it gave me a 0.94. I think this was what I selected was AUC. So it gave me a value of 0.94. Yep, AUC weighted. So that was a primary metric. So based on that, it said that this was the one that returned the best value. And if I go check out what are the models that it tried, so these are all the models that it tried. And this is sorted by AUC weighted, and it shows you how long each ran, so it's like a minute, yeah, roughly about 1 minute each of them. It went through, it doesn't give me a count, but it went through quite a lot of these models, maybe a few dozen models as well. And if I go and ask it to show me the model details, so whatever was selected, so let me go and see the visualization. So if I want to see how well this model performed, so this is a precision recall curve. This is an ROC curve, calibration curve, confusion metrics, and these are the counts of all of the false positives, true positives, false negatives, true negatives. So all of these counts are given over here. So you can actually see this against every model run that was shown over there. So the, I don't know, 30 or 40 model runs that were shown there, you can actually see the performance of each model. And for each model, it obviously went through many different runs. Again, this is one of the parameters you can specify. How many runs is it going to go through for each model to get to a state of convergence? Okay, so this was using the UI. I have the same thing that I can show over here. So over here, I have in notebooks. I said I have certain notebooks over here. Okay, so I used one of the pre-made tutorials because I'm being a bit conscious of time and I want to give some time. So one thing that I copied already was this notebook. So I showed you an example of classification one. This is a regression AutoML solution. And over here, this we use regression analysis to predict taxi fares in the city of New York. So I can open this in, it's a little difficult navigating. I can run this over here, but it's a little difficult running it over here. So I actually can open this in Jupyter Lab.
Quick question.
Yeah.
How long did it take the whole the classification?
I believe I set a time limit of 2 hours for it to run 2 hours, and it did within 2 hours. Yeah.
Like 40 models.
Yeah, but the data set is not that big. Yeah, so the data set is not that great, and also it depends on which machine you're running it. So the compute that I had used had probably like 4 GB of RAM, 2 CPU. So it wasn't that powerful either, because it was something that I was, again, using a cloud resource to actually spin up and have this model run training. Okay, so this is another one. So this is again another AutoML, but this time we're actually not using the UI or that option in the solution to do. We're actually writing our own code over here. So in the first step, we're actually doing a lot of preparing the data. So we're downloading the data. The data set that's being used is part of the Azure ML library already. So if you go from Azure ML.open datasets, you're actually bringing this dataset, New York City TLC green. So you import this. In the beginning, they actually do lots of data manipulation. They're bringing data in cycles and they're loading it into a data frame over here. And then slowly by slowly, they actually do different things to the data frame. So the first thing that they do is actually say, okay, we don't need all of these columns, so they drop certain columns. And then once they have the right columns, and they say, okay, we want to find out seasonality, so they're calculating like the day of week and the month and the year and the week number and so on and so forth. They actually do that calculations over here. And yeah, then they do some data cleansing. Through some simple statistical analysis, they find outliers, they find things rows which are not really needed. So they do some of that cleaning over here. And finally, they're happy. Okay, this is the data set that we need. Now, in order to run the AutoML cycle, they create a workspace. They split the data into a training set and into a test set, and then they train the model. So this is where the AutoML cycle actually starts. So in order to train it, you actually need to define certain configuration parameters. These are the ones which I forgot to show you when I was creating that experiment. So you show what is the iteration timeout in minutes, how long should each iteration take, the number of iterations you should have each model going, what the primary metric is over there, because that was a classification, we use AUC. Over here they say the spearmint correlation, so finding out the correlation between two features or two columns, how closely correlated they are. Do you want to do some pre-processing? Is where this is where your question may be answered, where if by setting this to true, the experiment can pre-process the input data, handle missing data, converting text to numeric. So it's not tied to the model itself, but it is generating some data preparation, pre-processing also, irrespective of the model that gets selected. So there seems to be some ability to do that. And then the verbosity, this is the logging, and the number of cross-validations that need to be done. So these are all parameters that you specify for the AutoML cycle. They have nothing to do with the model itself. Yeah, and then you do you configure things, and then you train. And I've already run this, like I said, a couple of nights ago. So the logs are present. You can see this is how it's actually started to process this. And it took me again a couple of hours for this to run. I don't remember how long. But no, this actually took shorter because it was a different model. The classification one took a couple of hours. This actually ended up in like 30 or 40 minutes. One reason is because I doubled the computing power on this one. So this ran on an engine that was twice as powerful as the classification one, but I think it's also because there was less algorithms that it went. We specified 20, so it just went with 20 of them. There may have been more of them. And each one was taking less than a minute to run. So these are the ones that I tried out. This is my measure. So it gave me different results. And as it was going through each one of them, it figured out which one was the best. So this one was the best. Min, max, scalar, random forest. Okay. 19475, and yeah. Usually the best model. Then you're testing, so once you have the training done, then you actually do the testing of that trained model or the best model. And you come up with the results. So again, I'm going through it very quickly, but this solution is already there, and it's very easy for someone to try it out and actually experiment and see how it performs. And the third way that I'd like to show, and this is the last thing that I want to do cover today, is what if I wanted to do this in my application, in my C# application. So that is also provided. So Microsoft, if you go on the GitHub site for Azure Machine Learning, so there are lots of code samples present over there as well, and I'll show you one of the links. So over there I found a project, a Visual Studio solution, that embeds AutoML in your C# application. So the code for that is given over here. So you can see that this is the file, this is part of the data set. So when you download that project, the data set comes with it. So you can pick up the data set, you can do certain operations on the data. I won't go through the code itself, but you can see it's not that big. And what this does is it calls ML.NET, which is Microsoft's machine learning library or framework, and it's getting pretty sophisticated. They started this out not too long ago, a couple of years to 3 years ago, but in the past year it's really taken off because they've implemented a lot of algorithms, they're constantly adding new things. They had their, they come up with a release pretty much every month or so. So right now they're at 1.something version that's going on. And it's an open source project, so you can actually do that. At one point in time I was thinking if I had time I would contribute to that project because it is pretty cool. And participating in something that has recently started out is always fun. So yeah, so this is the code for actually doing pretty much what I showed you right now in the Jupyter notebook, and before that in the UI. This is the code that does all of that. The documentation for ML.NET is given over here. So you can navigate to .NET/Microsoft Learning, machine learning, and over here you'll actually see MLNet, and this shows you pretty much all of this. So how to use MLNet automated machine learning API. So this gives you all of that information that I just showed you in a GitHub, in a Visual Studio project. Including an explanation of all the parameters. So for example, if you're doing binary classification, one of the metrics that you can actually have based on which you can gauge the success or the efficiency of any model. And then if you're doing a multi-classification, multi-class classification, then these are the measures, and if you're doing regression analysis, then these are the ones that you can use. Now there is some difference between what ML.NET supports, and I believe what other versions of AutoML actually are supported. And I'm not sure, I've not fully explored it, but I think there is some difference. So I've seen some metrics being used which are not present in ML.NET. So there may be convergence coming, but I think there is some slight difference. And finally, all of the resources I showed, you can actually go through this URL link. It will point you to AutoML, and the material is all out there. I mean, I took this and I browsed it. I spent some time learning about it. It was so easy. The tutorials are there. All you need to do is have an Azure subscription. I don't even think you need to have money in your account in order to use that, because this is all at a preview. It's all free to use, and it makes the process of learning machine learning so much simpler, so that you don't have to spend a lot of time figuring things out in order to bring that capability into your product. Thank you.
I just have a question. So like how much prior machine learning knowledge do I need in order to learn this?
You don't need a lot. That's the whole idea behind this. So for example, all of these algorithms, I don't know quite a lot of them either. And I don't know how they work. I just know that through this, I've been given, after a scan of hundreds of algorithms, which I could never have done on my own, a subset of algorithms which are ideally suited to solve a certain problem that I am. And then I can fiddle around with a little bit more. But yeah, the whole point is that you don't need to have a lot of knowledge, and you can very quickly bring this into your product. So let's suppose if I was a software engineer and I wanted to bring in certain machine learning capabilities, then all I need to do is write this 500-line code program as a class in the rest of my application. And that would take care of the machine learning portion. And wherever the machine learning model has been trained, then I can deploy it. I didn't show you the deployment portion, but for deployment, all you have to do is, so once I'm fine with my model, so you should show it to experiments. So this is the one that I ran. So once I'm fine with this, all I have to do is select this, deploy best model. So it's at the bottom of the screen. Here. So all I do is just press this, and it would deploy this model to the resource that I tell it to deploy on Azure, and that comes up over here. So again, the process of the machine learning portion has been simplified greatly, and then once you deploy it, then you consume it in your application.
Does it say for for each proposed model, yeah, because it gives the best one and then other ones. Does it say what features were considered? I mean, one model might consider some features, another one another ones?
No, it does not. So the details are just provided in that visualization, that these are the things that were, this is through going through many different runs, it was able to get to a certain stage of whatever your measure was. But I don't think so it says that these are the features that I selected in order to get that or not. Probably it consumes all of them. So if I could generalize the question, what we're saying is that are all the training of all the models, are they done similarly, or is there some intelligence that between model variations you're able to determine that this is the optimum mechanism that I should be using in order to get to a certain stage? I don't think so. Yeah, I don't fully know, but I doubt it. At least to the brief experiments I've done, unless someone has better knowledge than me on this. Yeah. Sorry, here's the question, then I'll move.
So my question is like, like this whole process pretty much sums up the work of a data scientist, right?
Mhm.
So like, would the job of a data scientist go extinct or something with
No.
this process?
No, the job of data scientist is not going to go extinct because whenever you have automation, right, automation is not the solution to every single problem out there. So, for example, mass production of industry goods, right? Does that reduce the need for people who prefer customization or prefer something that is a little more specialized or tailored? No, the answer is no. There is always a need for people to actually excel in a certain area, and then for the masses, we can have automation who don't really need something that is expensively built just for them. So hundreds of companies out there just need machine learning model that can bring certain intelligence to what they want to do in the business decision making. But there will be other companies out there who need to have that specialized talent. I'll give you an example that we see right now. So you have these common frameworks. You have, for example, Azure Cognitive Services. You have speech to text conversion over there. So that's already there. But you have natural language processing. That's already there. Now, does that mean that every individual who did NLP engineers, are they out of this? Are they out of the job? The answer is no. You have NLP engineers required who are specializing in certain vocabulary or specializing for certain domains because there is domain-specific knowledge. So Azure is not focusing on each individual domain. It's just offering a general platform that does NLP. So if I want to develop a simple chatbot, I'll use one of those pre-trained models which are good enough in the space that I am. But there are lots of companies for which that is not good enough. So yeah, there will always be need for data scientists and people who specialize in really cool stuff. But for the masses, something like this would actually suffice. So you had a question.
Yeah, so I used to think AutoML is all about hyperparameter optimization.
Mhm.
Like, in a random forest choosing the number of trees or choosing the depth of trees, number of trees. So you're saying AutoML also includes selection of different algorithms?
Yes. So not just does it do that, so it also goes and chooses different algorithms over there, yes. So it's a nested, if you will, it's a nested iteration, where for each cycle of algorithm, it will go within an algorithm and go through each cycle of, for example, parameter optimization. And there may be an aspect of feature engineering as well, which I'm not really sure. In theory, it has to be. So you're actually converting the features for the algorithm that you'll be using, and then within that will be for the parameters that you'll be trying to optimize. So there may be multiple nested layers in the iteration as well. You had one question, and then I guess I'm going to take 3 more questions, and then maybe we should wind up. Yeah, sorry.
Have you compared the performance of this currently to the same data set and you manually choosing a model and optimizing yourself? For example, the one you showed us, it automatically picked random forest.
Mm-hmm.
So if you were to do it yourself, you probably would have at least came up with or tried the idea of doing back decision trees yourself.
Mm-hmm.
So if you did that and optimized it yourself, would you have gone similar performance? Would it have been better?
Yeah, I have not tried it out myself. I have friends who are actually working on this or trying to do a comparison, so they've not really gone very far ahead. But they're trying to actually, one of my friends is trying to come up with his own AutoML framework. So he has these pre-built frameworks, and he's trying to just create a layer on top of that cycles through all of them. And he's trying to do something similar just to see how much better this is going to be, how much better it helps you get to an end state. I don't know, I don't have an answer, but I will ask that question for him just to see how advantageous this has been.
I'm not sure if you actually started to touch on this, but have you considered auto feature engineering with AutoML as a means of discovering significant aspects of the data?
I'm not familiar with the space of auto feature engineering, so that's maybe something I should take a look at. But thanks for bringing it up, yeah. Okay, can you tell me a little bit about auto feature engineering? Or?
We were just starting to look at it ourselves.
Okay.
And so I'm part of the data platform for House AI.
Okay.
So we were looking at can we get better insight into data that we have no history on.
Oh, that's pretty cool. Maybe I'll have to chat with you some more during the break. Yeah. Thank you. So, one last question because we really need to start. Yeah.
This is a quick question. From your experience does it pick one algorithm, or can it give you a combination of an ensemble of algorithms from
So-
the options data?
I don't honestly know. My guess is that it has this ensemble algorithms which is already present out there. So it doesn't dynamically combine two of them and see, oh, let me try this and see if it works. My guess is that these are combinations which are already present, and it's just iterating through all of them. Yeah. And one thing that I did not show, but one of the things that you can try out is you can also exclude algorithm. So if you know, for example, that this data set is not going to be good for these subcategory of algorithms, you can actually specify that in your exclusion criteria and just exclude it. Okay.
So
Slava,
is
yeah.
it possible to specify correlation metric along with the objective function?
So there was an idea of selecting a evaluation metric, which is the one that you actually is going to be criteria based on which it's going to propose the best recommended model. Yeah. Really?
Yeah, cool. Thank you.
Thanks, guys.